All right, so what we're going to do is look at today the law of conservation of momentum applied to collisions. So there are going to be three types of collisions that you could potentially see pertaining to the law of conservation of momentum, and that is what's called first an elastic collision, then we have an inelastic collision, and we're also going to look at the case of what I like to call an explosion. So an elastic collision is where we're going to see two things hit and bounce. The key thing is that we have here two separate objects, so object 1 and object 2. They're going to collide and then they're going to separate. So elastic means they're going to bounce. Think of that word. Elastic means for something to return back to its original position. Same type of collision that we have is what's called an inelastic collision. So this would be considered a hit and stick. So instead of bouncing, in as a prefix means not elastic, so they're not going to bounce, which means they're going to collide and move together as one object. The last type of collision we have is what's called an explosion. So explosion or recoil is just a case in which we have the objects starting together. So it's like the opposite of an inelastic collision. They start together and then they separate. What makes an explosion unique is that when they start together before the explosion, more than likely sometimes that initial momentum is zero, which means that their final momentum based on the law of conservation must also have to equal zero. The confusing thing is that we have two objects then after this explosion that are going to be moving, but essentially in an explosion, you have one object moving in one direction. You'll see here that the cannon itself is moving in the opposite direction. So that's something also called recoil, because that's like when you fire something and it recoils back is when it's going to move back in the opposite direction, and that is due to the law of conservation momentum. So our goal is to analyze these types of problems using those same two-way tables showing the law of conservation momentum, but with those individual types of collisions. So here I have a girl catching a medicine ball, and says the girl is also on ice. So she's going to catch the ball and they're going to slide together on the ice afterwards. And our goal is to use this information to determine the velocity of the girl and the ball after the collision. So in terms of her catching the ball, when you catch something, obviously you're going to hold on to that object, so you're going to move together. So this is like a stick collision, or what's called an inelastic collision. So if I want to find the momentum before and after, again, all I have to do is use my momentum equation of m times v. So you're given the mass and speed of both the ball and the girl beforehand, and again, we're going to fill those things out in my table. So just so we don't get confused, object 1 is the girl, object 2 is the ball. So initially the girl has no momentum because she's not moving, and the ball, moving with a speed of kilometers per hour and 15 kilograms, would have an overall momentum of 300 units. And I know the units of kilometers per hour is not really matching up with our meters per second, but we're just going to look at values here, look at the magnitude of these things. The ball is moving to the right, so again, we can think about this as a positive 300 units. So which means the total momentum, again, is going to be 300, which means that afterwards, those momentum have to be equal based on the law of conservation of momentum. So my goal then is to figure out what is the speed at which these objects are going to move. So we know that the mass of each object, the ball is 15, the girl is 60. So in order to find the momentum afterwards, we're going to have to compare the masses. Okay, so I know that they have to add up to 300 units, but essentially what's happening here is that both the medicine ball and the girl are moving with some velocity that we don't know. But the idea is that the two objects are moving together as one. So what we're going to do is we're actually going to take those masses and add them up. So 15 plus 60 would give me a total of 75 kilograms. And we're going to think of 75 kilograms as the total mass. They're going to move together with some speed, and their overall momentum has to equal 300, which is the total momentum of the system. So that would then tell me that the speed at which they're both moving has to be 4 meters per second. Okay? So right away there I can solve for the speed, which is part of this problem. But I'm going to continue on showing this table, or the truth table of the conservation momentum, so we can see kind of what's going on with each object. So I know that the ball has a mass of 15 and a speed of 4, so its momentum is going to go down to 60 units. So overall, it's going to lose 240 units of momentum. And the girl having a mass of 60 and moving at that speed of 4 is going to have a total of 240 units. But she's going to gain that 240 since her original was 0. And then again, the overall change is going to be 0 because if you add 240 and negative 240, you're going to get 0. And again, to show the conservation momentum, we see this last row here where the initial equals the final. My overall change is 0. And you can also look at, if you were to add the afterwards 240 and 60, those should also give you 400 or 300. So everything works out here again in terms of the conservation momentum. All right, so again, now this is kind of similar. So why don't you guys try this one on your own. We have a baseball moving at a certain speed, crosses the plate and strikes the catcher's mitt, which is originally at rest. It says determine the post-collision velocity of the ball and the mitt. So our goal is to fill out this table and determine the speed of the ball after the catch. So why don't you guys pause this and try this on your own. Okay, so just analyzing to start by using the mass and the speed. I know that the ball is going to have initial momentum of 6.75. Says that the mitt is at rest, so they have 0. So in total, we know to have 6.75, because if I were to add these two values together, that's what I'd get. So then after collision, again, it's got to be the same based on the law of conservation momentum. So what we have to do is find the individual momentums of both the ball and the mitt. So what I did is, again, since it's an inelastic collision here where they're both moving with the same speed or moving together afterwards, what I did is I wanted to find that speed. So since they're moving together, I added the masses together to find that it'd be 0.4 kilograms. Then I got to think about what speed would give me 6.75 units of momentum. So they're going to move backwards, both the ball and the mitt, with 16.875 meters per second of speed. So to find the momentum of each object afterwards, I have to take their individual mass times the speed of 16.875 and know that this speed, again, is going to be the same for both objects. All right, so with a little bit of rounding with the ball, I should get about 2.53 units of momentum afterwards. For the mitt, I would have 4.22 units of momentum afterwards. And again, if you add these two numbers, it should give you 6.75. So then if I want to find the change again, the change is always going to equal the final minus the initial. So I know that the ball is going to lose momentum. The mitt is going to gain momentum. So the mitt is obviously, you can see, is going to gain 4.22 units of momentum. And if you were to subtract those values, the ball is going to lose 4.22 units of momentum for an overall change of 0. So not the prettiest numbers here, but again, we see that the total's equal and that overall change is equal to 0, so that's the law of conservation momentum. All right, so now let's try a case of when two objects separate. So here I have a truck and a car colliding. Truck's moving, car's at rest. Afterwards, they're going to separate, so this would be an example of an elastic collision where they're going to hit and bounce. So again, we can use this two-way table to analyze the momentum before and after. So using the values given in the problem, okay, so based on the values before the collision, the truck would have 30,000 units of momentum, the car would have 0 units of momentum for a total of 30,000. Based on the information given here, I know that the car is going to have 15,000 units of momentum. So if the total's got to equal 30, I know that the truck has to also have 15,000 units of momentum. So again, looking at the change, I know that the truck here is going to lose 15,000 units. The car is going to gain 15,000 units for an overall change equal to 0. Now this one's a little bit different. Notice I could fill out the table without knowing the speed, but now that I know that the truck after the collision has a momentum of 15,000, I can use that plus the information here to find the speed. So then I got to know, okay, if the truck is 3,000 kilograms, what speed would give me an overall momentum of 15,000 units? And that would give me obviously an overall speed of 5 meters per second. So the truck is going to lose about 5 meters per second of speed while the car is going to gain 15. And again, that difference in speed is going to be because of the mass. So this would be an example of an elastic collision. They solved a little bit differently, but again, using our table to understand how we're solving. Okay, this will be our last example. So what I have here, a 1.5 kilogram cannon is mounted on top of a 2.0 kilogram cart and loaded with a tennis ball. So you'll see here that all three objects are loaded together. You can see here this is going to be an explosion, so we know that the tennis ball is going to shoot outward, and at the same time the cannon and the cart are going to recoil backwards. So think about here that after the explosion, the ball is going to move to the right and the cannon and cart are going to move to the left. So this is what's going to happen in an explosion. You might have heard of that idea of recoils when things are going to start together and separate. Can also think of this as like the opposite of an inelastic collision because they start together and then they go separate in the end. But again, what we're going to do is analyze this using the conservation momentum. So we'll look at the momentum of each object before and after. We'll say that object 1 here is going to be, let's say, the cart in the cannon. So I'll label this in red. And then we'll say object 2 is the tennis ball, label that here in blue. Okay. So before the collision, it says that each of these 3 objects are all moving together with a speed of 1.27 meters per second. That means both the cart and cannon and the ball are going to have individual momentum. So to solve for that, I'm going to take first the cart and the cannon. So that's going to be a total mass of 1.5 and 2.0. I'm going to multiply by that speed of 1.27. So notice here I'm just combining the masses because it's 2 objects moving together. So when I do that, I'm going to get 4.445. Okay, so that's going to be the momentum of the cannon and cart before the collision or before the explosion. The tennis ball has its own mass of 0.05 kilograms. I'm going to multiply that with the same speed. And again, I'm going to use the same speed because they're moving together as one. And that's going to give me 0.0635. And then if I want to find the total momentum again, what I'm going to do is add those 2 individual momentums together. Okay, I'm going to round this final answer to 4.5. So 4.5 is going to be the total momentum before. And now with the explosion, that means the afterwards is also going to be 4.5 because, again, momentum needs to be conserved. Now what happens after the explosion is that the tennis ball is going to be shot outward, and the tennis ball says reaches a speed of 75 meters per second. And then we need to find what is the post-explosion speed of the cannon and the cart. So the cannonball afterwards, again, is going to have that same mass of 0.05, but now it's moving at a speed of 75 meters per second. So that's a lot of speed. In terms of total momentum, that's going to give me 3.75 for the overall momentum of the tennis ball. So again, what has to happen here is that the cart and the cannon, are going to have a certain momentum that would then add up to 4.5. So that means the cart and the cannon have to have an overall momentum combined of 0.75. That's going to get me to add to 4.5. So again, the 2 individual momentums have to add to the total. So now what we can do is we can think about, okay, if the cart and the cannon have an overall momentum of 0.75, essentially what we got to do is think about, okay, if I look at the combined masses of both the cart and the cannon, I want to know times what speed would give me a momentum of 0.75. So right now I can start to think about the speed at which those 2 things would recoil. Okay, and that would give me, if I solve for V by just dividing by 3.5, which is total mass, I would give a post-explosion speed of 0.21 meters per second. So the 2 objects are going to slow down considerably, and again, that is because the tennis ball's mass is so much less compared to those 2 objects. And then again, to complete our table, looking at the change, again, the change is going to look at the final minus the initial. So I'm just going to round these answers for you guys. So the cart and cannon are going to, in this case, lose about 3.7 units of momentum. And the tennis ball itself is going to gain 3.7 units of momentum, so that the overall change of both the cart, cannon, and ball, the overall change of momentum for the entire system is going to be 0. Okay, so this was an explosion. Again, we solved it very similar to how we did it in Inelastic and Elastic Collision. It's just now we're looking at things as they're combined as one, but we can still analyze them separately using mass and speed. So again, this is looking at the different types of collisions you can have and how the law of conservation momentum applies. If you guys got any questions, make sure you jot those things down, bring them to class. We'll see you guys in class. Peace.